Okay. Ready for chapter 14? So yeah, if we can get in a good hour. If you feel like, or if I want to take a break in 20 minutes or so, maybe I will. But let's get into this. We're doing great. I think as long as I'm not as long as you're not getting more information than you can process, or at least digest a little bit later. Get enough of it right now that you can digest it later. You ready to shift over to carboxylic acids? There's a couple chapters here that are favorites. Carboxylic acids and esters is a neat chapter. Sugars is a neat chapter. Protein is a neat chapter. I mean, they're all great. So, carboxylic acid. This chapter is going to be carboxylic acids and esters. It's going to kind of break up into those two parts. We're going to start here. We won't introduce esters for a little bit. You make esters from carboxylic acids. So before we can get to esters, we have to get pretty familiar with carboxylic acids. All right, there's the carboxyl group, the COOH group. And what that COOH group is a carbon-oxygen double bond and a OH on the same carbon. This is what makes a carboxylic acid. In other words, if I had a molecule like this, that is not a carboxylic acid. That's an alcohol and, let's say, an aldehyde functional molecule simultaneously. But it's not going to be acidic. What makes carboxylic acids acidic? This hydrogen right here. Yeah, that hydrogen is the acidic hydrogen. We'll see it. What it means is it actually dissociates. You put a carboxylic acid in water, and that hydrogen comes off of there as a free proton, making the water acidic. So these are weak acids. They are naturally occurring. Vinegar is a very common carboxylic acid. It's acetic acid. Vinegar is about, what you buy in HEB is about 5% acetic acid in water. So it's 95% water, 5% acetic acid. You can, sometimes when people are pickling things, they'll buy, I think, 9%. It's like 9% acetic acid. So a little stronger, a little more concentrated vinegar. Lemons and citrus fruits have citric acid. Apples, malic acid. So there's a whole family of carboxylic acids that are naturally occurring, and then a whole ton more that are man-made carboxylic acids. Yeah, so acetic acid or vinegar has been known for a long time. So here's an organic molecule that people have been aware of for centuries. So these are very common, well-known molecules. Yeah, so they contain two very polar functional groups on the same carbon. You've got a carbonyl and a hydroxyl on the same carbon. These are more polar than alcohols. Of all the things we've talked about so far and said, this is more polar than that, alcohols are more polar than aldehydes and ketones, carboxylic acids are more polar than any of those. They're the most polar. You've got a carbon here with two oxygens on it. And they're just pulling the electrons to these oxygens, so much so that it leaves this thing kind of hardly attached. You put it in water and it dissociates. So here we'll talk about 3x5 cards here in a minute, but this is obviously one of them. Acetic acid is the common name of the carboxylic acid in vinegar. The IUPAC name, 2 carbons, ethane, it's ethanoic acid. Ethanoic. All right, so we'll talk about naming here in a minute, but there's a kind of a preview. Here's a 3 carbon. Propanoic. So propane, we drop the E and add OIC, and we get propanoic acid. 1, 2, 3. We got the carboxyl group on the end. We don't need to call it 1 propanoic acid because there's no way of getting that really in the middle of the chain, along the chain. Because look, after you get those 2 bonds and that bond, there's only 1 bond left. So this thing has to be on an end. So propanoic acid, we know that the carboxyl group's going to be on the end. Butanoic acid, hexanoic acid, it's going to be on the end. And there's another common name. Propionic is the common. This is IUPAC. Okay. Okay, we always kind of talk a little bit about what are the properties of these things. As I mentioned, they're more polar than other things. And usually if we put a dividing line down through here, what we're showing here on the left is if we had a bottle of just pure acetic acid, for example, no water, just pure acetic acid. The acetic acid molecules would hydrogen bond with each other. You got an OH group on the carboxylic acid. You got an OH group on the other one. So the oxygen on the one would line up with a hydrogen bond. It would hydrogen bond to that hydrogen. And this oxygen would hydrogen bond to that one, and you could even have the hydrogen on another carboxylic acid hydrogen bond to the carbonyl. So one molecule could actually get as many as 3 hydrogen bonds with other molecules around it. All right, so in the same sense that this OH bond on the carboxylic acid is a polar bond, so is the OH bond on water. So the water molecules can hydrogen bond here, a hydrogen can hydrogen bond there, a hydrogen can, on the water, can hydrogen bond to the carbonyl. This is why like dissolves like. The water molecules are behaving just, they could replace these hydrogen bonds here. And the molecule is attracted to the water like it is attracted to itself. And so there's a polar solvent dissolving in a polar substance, or a polar substance dissolving in a polar solvent, water. Like dissolves like. Polar will dissolve in polar. All right. You expected this, right? Boiling points. As soon as I talk about polarity of molecules, I'm going to mention some boiling points. But before we look at the boiling points, we're trying to gather up molecules here that are about the same weight, molecular weight. And here's an alkane. So we have an alkane here. We have, I'm going to just kind of skip over it. There's the ether, but don't worry too much about the ether. Here's your aldehyde. Here's your ketone, roughly 50 degrees centigrade. Don't get hung up on these exact numbers, just roughly what is the boiling point. Here's your alcohol. So we're going from about 0 up to 50, up to almost 100. And now the carboxylic acid, almost 120. 20 degrees higher boiling point than a comparably weighing alcohol. And what does that tell you? The higher the boiling point, the stronger the attraction those molecules have for one another. Therefore, it takes more energy to overcome that attraction and get them to boil. All right, so the most polar, which corresponds to the highest boiling point. All right? So we've done this each time with each of these categories and just kind of shown how boiling points is giving us a little window into how strongly the molecules are attracted to one another. Nomenclature. How do we name carboxylic acids? Well, IUPAC rule number 1 is what? Find the longest chain. So no matter what class of organic compound you're talking about, find the longest chain that includes that new functional group there, the carboxyl group. And this is going to be carbon number 1, 2, 3, 4. So it's 4 carbons long, so you would think of butane, but this isn't butane, it's a carboxylic acid, so we're going to drop the E and add OIC, and we get butanoic acid. And the bromine is on carbon number 3, so do we have the name here? Neither one of these slides has the name, so it's going to be 3 bromo butanoic, and we include now acid, butanoic acid. All right? And it's got a little comment there. If there are 2 carboxyl groups, you would say dioic. So let's see if there's, yeah, I think we have some examples here. So there's our two carbons. Ethane becomes ethanoic. 3 carbons. Propane becomes propanoic. 3-methylbutanoic. All right, here is, now adipic, I mentioned on that first slide. Which fruit does that come in? Oh, maybe I didn't mention it. Adipic acid is, trying to think what fruit. The orange? I think this is a naturally occurring carboxylic acid. And we've got a carboxyl group on either end. So it's 1, 2, 3, 4, 5, 6. We're counting these carbons as part of the chain. Don't just count this. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Hexane dioic acid. So it's got 2 carboxyl groups. I believe there's another slide where we can capture all the ones with IUPAC and common names that I want you. Yeah, there you go. There it is right there. This is a great slide. All right. So this one, this one, this one, this one, this one, and this one. You should know both of their names. Wait a minute. No, just, yeah, these here, you don't really need to know these names. Stearic acid is octadecanoic. It's 18 carbons long. So deca, 10, 8 more, octadecanoic acid. These two, just know their name, and we'll look at these in a little bit more detail here. Let's look at the top. Let's kind of start at the top and go down. Formic acid. Now in chapter 13, you learned formaldehyde, right? 1 carbon. It was a 1 carbon aldehyde. Formic acid is a 1 carbon carboxylic acid. That's its common name. Its IUPAC name is methanoic. 1 carbon. Methane, methanoic. Okay, now here's a little bit of, this comes free of charge. Formica. Ants, so fire ants bite you. And it burns and itches and you're scratching. Why? Because they've deposited formic acid. When they bit you, they deposited some formic acid there. Do you think an acid would be a great thing to have in a scratch or a burn or you think an acid would? No. It would burn. Acids would burn if they get into a scratch. Well, the ant has kind of broken the skin and left a little bit of acid. So the remedy for that is to go get some baking soda. Some baking soda and water. Just make up a little quick solution of baking soda and water and wipe it on where the fire ants have bit you, and it will neutralize the formic acid. Take away the itch. Now it'll either work or you will think it worked and it'll stop itching. Either way, you're in better shape, right? Because the worst thing is that you just don't know what to do about it. Well, now you know something to do about it. Baking soda is a weak base. Formic acid is a weak acid, and they will form sodium formate. And it won't itch as bad. Acetic acid, we said, is vinegar. I know what they're doing. This is the Greek words that they're coming from. Greek words. Propanoic acid, so Swiss cheese has a little bit of propanoic acid in it. So it's called propionic, propanoic. Butanoic acid is also butyric acid. Butanal is also called butyraldehyde. So BUTYR is a common prefix for 4. So whenever you see butyraldehyde, butyric acid, butyrate, you're talking about 4 carbons. And when butter goes bad, that's what's being formed in the butter, is butanoic acid. All right, we'll look at, I think the next couple slides are going to look at these. These are fatty acids. These are fatty acids. We will talk about these a lot more in chapter 17 when we get to biochemistry, because these are major components of lipids, and particularly triglycerides. So the triglycerides, like olive oil, is a triglyceride. It's a bottle full of triglycerides. And it has certain fatty acids in it. So we'll learn more about them, but let's just get a little idea of what these fatty acids are here in a minute. Okay, adipic acid, That's your hexane dioic. It comes from beets. There we go. I knew I had it somewhere. Citric acid. Now, I said these are always on the end. This is one where you might say, well, what about that? That is not on an end, but it's not in the chain either. It's hanging off of the chain. So that one would be a hard one to come up with an IUPAC name for it. So hence citric acid. So that's what's in oranges and lemons and limes, citric acid. Yogurt, lactic acid. So it's in yogurt, and I guess that's also what's being formed when you exercise really hard and your muscles get sore. You produce so much lactic acid that your body is trying to get that out of the muscles. And that's what you form, lactic acid.
Do we need to
Memorize these? No. No, you don't need to memorize these. Here's the ones that you need to memorize. Now, yeah, so you need to, we're going to look at the structures of oleic and stearic here in a minute. I don't know what slide to get to, but we'll get to them. All right. Naming carboxylic acids. Yeah, I'll tell you what. Let's name these and take a break. So till about not quite 10 after, we'll come back and name all of those. But you try to name those.